Hello, everybody. In this episode, I'll be speaking with David Lindner. David is a research scientist in the Google DeepMind AGI Safety and Alignment team. Links to what we're discussing are in the description, and you can read a transcript at axrp.net. You can also become a patron at patreon.com/axrpodcast. All right, welcome, David.
Yeah, excited to be here.
Yeah, so I guess in this episode, we're going to be chatting about your paper Mona, Myopic Optimization with Non-myopic Approval Can Mitigate Multi-Step Reward Hacking. So this is by Sebastian Farquhar, Vikrant Varma, yourself, David Elson, Caleb Bidulph, Ian Goodfellow, and Rohan Shah. So yeah, to kick us off, just what's the idea of this paper? What does it do?
Yeah, so the basic question that we're trying to address in this paper is how can we prevent bad behavior in AI systems even if we don't notice it? So that's particularly relevant for kind of superhuman AI systems when the humans might not be able anymore to detect all of the bad behavior we want to prevent.
In particular, so sometimes in the alignment community, people break down like two types of bad behavior, causes of bad behavior. There's like bad behavior that was incentivized or that was rewarded during training that was upweighted. And there's like bad behavior that comes from like inductive biases of like the model just like starts off wanting something bad and then it just like plays nice and it's never actually rewarded for doing bad stuff, but it's never like in kind of it just keeps on being bad even though these are often called like outer and inner misalignment respectively. Am I right to think that your paper is mostly about outer?
Yeah, that's right.
Okay, sure. So yeah, what's the idea? How are you preventing this?
Yeah, so the basic idea is to restrict AI systems or incentivize AI systems to only pursue strategies that humans can understand and can oversee.
Okay.
And yeah, so we do this by restricting the kind of planning ability of agents and training them myopically, but with a type of feedback that is kind of forward-looking that for example, can come from humans. So this is the feedback rewards plans that are good according to the human and that humans understand. So it's still kind of rewarding good long-term plans, but it does not reward plans that humans don't understand, which includes kind of potentially bad or reward hacking plans.
Yeah. So my understanding of the setup is that roughly you're kind of giving AIs this sort of single shot reward. So at each time step, which we can talk about later, like the AI gets some reward just for sort of concretely how well it did at the task. And also it gets some sort of reward that's basically a proxy of, okay, according to humans, how much sense does this make? Does this action make long term? And it's sort of being incentivized to at each time step output an action. Like it's being trained so that at each time step it's trying to it's supposed to be outputting an action that maximizes kind of the sum of both of these rewards. That's my understanding. Does that sound correct?
Yeah, that's right. I think the instantaneous reward you can often think about as mostly evaluating the outcomes. So often kind of for the intermediate plans, it will be kind of zero because it's not achieving the outcome yet. And this kind of non-myopic approval reward, how we call it, is mostly about evaluating the kind of long-term impact of an intermediate action.
Why does this prevent bad behavior by AIs?
Yeah, so basically it doesn't, so first of all, it doesn't prevent all bad behavior. So within one step, the agent can still kind of be incentivized to like try to get high approval via bad means. But the specific kind of bad behavior that we're trying to prevent is multi-step reward hacking or kind of more long-term bad behavior. So specifically the agent kind of setting up a plan to achieve high reward in the future. So like an example of that is kind of tampering with your own reward signal to make it easier to achieve high reward in the future. And so, yeah, the reason this scheme prevents that is that there is no longer kind of a connection, or we no longer kind of backpropagate the future rewards to the current action. So the current action is not incentivized by this future reward. And if the human doesn't understand, or the kind of oversight mechanism doesn't understand how this reward hacking happens, then by default, this plan will not be incentivized.
Or the way I'm thinking about it is, okay, suppose you sort of, like why does an agent try to tamper with its reward function? Well, it's got to be the case that at some time, right, it's like doing the tampering, it's putting the investment in, so that later it's able to like get this high reward forever and ever. But you're only optimizing it to at each point do actions that make sense sort of at that time step. And like these sorts of, I think the idea is supposed to be that like in a bunch of cases, these sorts of like instantaneous, investments into a reward hacking feature, like they're not super highly rewarded in that time step, and hopefully like the non-myopic human approval like doesn't think that they're especially great, and therefore like it's never shaped, it's never like rewarded or upweighted for doing these sorts of like long-term investments, and like that's the reason it's not going to do these things in future. I don't know, maybe this is just like the thing you said, but this is the way I'm currently understanding it. Does that like...
Yeah. So I think this is basically right. So the reason we think this is the kind of like setup steps for multi-step reward hacking will not be rewarded is that they're like they will often kind of look very weird for the task you're trying to achieve. Where kind of I don't know, in the kind of maybe we will get into the examples in the paper a bit more, but kind of the way the kind of model does this type of reward tempering in kind of reality kind of looks really weird to humans, and humans would be kind of, even if they don't detect that there's the specific reward hacking strategy happen, they would at least be like, oh, this is weird, and I don't know why I should specifically upweight this. And if they kind of reward this lower than something else, it would not be incentivized or not be updated towards.
Gotcha. So I guess, maybe in order to just illustrate this, can you... So in the paper, you have a few examples of environments where you're using this reward setup. Can you talk us through maybe just one of them will suffice to kind of help give the audience a picture of like how this is really working?
Yeah, maybe because we're talking about the reward tempering, let's start with the test-driven development environment we have in the paper. This is basically supposed to be a model organism for this type of reward tempering, where we have a coding problem data set, and the agent gets kind of coding problems to solve, but we're trying to simulate a situation where the model designer does not have kind of a ground truth or way to evaluate if a solution is correct. So the developer relies on the AI system to provide its own kind of evaluation signal, in a sense. So this is a two-step environment where in the first step, the agent writes test cases, kind of unit tests that are supposed to kind of capture the problem and kind of turn the natural language problem description into unit tests as a problem specification. And then in the second step, the agent writes code to solve the problem. And the way the kind of reward is structured is that in the first step, the test cases are rewarded for being correct. So this is in a sense like a little bit of a suboptimal reward signal. So it's only rewarding correctness of the tests. And then in the second step, we reward the code, how well it passes the model written tests, because we don't have a better kind of reward signal to evaluate correctness. And so the reward hacking behavior that can happen here is the model writing kind of like softball tests that are trivially easy to pass. So like, if you run normal multi-turn RL on this, what will happen is that the model writes kind of often test cases that are only one special case, or like one corner case, something like an empty list as an input and 0 as an output for if it has to count something in a list or something, and then writes code that just returns 0 always. And that formally kind of gets high reward in this specification. But kind of with this kind of myopic optimization, this is no longer incentivized.
One thing I'm confused by is like, why isn't this incentivized in myopic optimization? So take the strategy of just like writing some very simple, easy to satisfy test cases that like, so the test cases, they're like correct but not exhaustive, right? Like, and so it seems like this strategy of, write very easy test cases and then write code that satisfies the test cases but doesn't actually satisfy the whole thing. It seems like even in the myopic setting, this is getting like perfect reward, right?
Yeah. So I think there's two answers here. So one thing is, I think in a kind of perfect or like kind of version that is exactly as described, where kind of exactly only correctness is rewarded, I think this still wouldn't happen. I think this strategy of writing kind of trivial test cases would be kind of rewarded similarly to other test cases, but there would be kind of an inductive bias in the model to kind of not do that initially, and there would be no kind of optimization pressure kind of away from this.
That's actually not so obvious to me. So like, if like in some ways those cases are the easiest to write, right? Like I don't know, if I'm like if you ask me, hey Daniel, can you write test cases for? Well, I guess it sort of depends, like what the background is, but at the very least, they're shortest. They're the shortest test
Yeah.
cases you can write, right? And they're also like the simplest, in some sense.
I agree. If we like had some kind of simplicity, like reward or something like this would like, yeah, probably this could still happen. But I think that so maybe the reason this I think this doesn't happen in our experiments is because we use kind of a language model autorator to rate correctness. And I don't think this language model autorator is perfectly, only looking at correctness, but it will actually also have some kind of bias towards like better test cases, kind of more comprehensive test cases. And so we didn't actually run an experiment where we only reward correctness, but we have this autorator, and I think that's probably the main reason this doesn't also happen in the myopic case. But this is, I mean, to be clear, this is somewhat intentional. So this is supposed to simulate kind of humans who like cannot perfectly evaluate this task, but are kind of like have a rough sense of like always having the same test case is kind of weird. So yeah, I think this is a reasonable model of this.
Yeah, I think actually just talking through this example is good because it kind of, okay, to put my cards on the table, I think Mona is like an interesting idea. I'm skeptical if it actually works. But part of my skepticism is just like, is it illustrated in this example? So talking you through it is like a good way to explore that. So yeah, there's sort of these two time steps, right? Like the first time step where the agent like writes the test cases, and the second time step where the agent writes the code that is supposed to pass the test cases. And in the first time step, it sounds like, yeah, the reason it doesn't write these trivial test cases is that, well, there are just all sorts of test cases it can write, and there's some auto grader for the test cases that cares about correctness, but also a bit about comprehensiveness, it sounds like.
Okay. So we instruct it to care about correctness, but I think implicitly it also cares about kind of comprehensiveness a little bit.
And then in the second case, yeah, the bad outcome is a model just like writes a thing that only fits the test cases and nothing else, and the good outcome is if the model writes a thing that cares about that just actually like solves the problem it was supposed to solve. And again, it kind of strikes me that this is a case where like even if you have test cases that are like a little bit more comprehensive than a little bit more comprehensive than just the absolute most trivial cases you can do, as long as they're sort of like, as long as you have like concrete lists and stuff, it seems like you could potentially just hard code the solving the test cases in the program you're supposed to write, right?
Yeah.
And that would be rewarded like just as well as actually solving the problem, if I understand the setup correctly.
That's right. So like this is actually happening sometimes in our experiments. Oh. So I think this is in the paper also. We have kind of a single step reward hacking solution that sometimes occurs. That's exactly that, where the model kind of still like, for some reason it happens more in the kind of ordinary RL than Mona, but it's not something that Mona is kind of supposed to fix. But what happens is, the model, even if it writes kind of test cases, it can that are correct or comprehensive, it can write a solution that is kind of, I don't know, it has like a special case statement for each input and produces this exact output.
Right.
We kind of prevent this from happening by kind of having kind of a length penalty on the solutions also. The basic argument here is that this kind of reward hacking is easier to detect and fix if it's happening in kind of a single step than if it's happening over multiple steps. So that's why, even if with Mona this still happens for this kind of second step, we think this is an advancement.
Yeah, what makes it easier to detect and fix this like single time step reward hacking?
I think that, so the general intuition is that models in a single time step have less kind of attack surface. There is less kind of, this maybe goes into like some discussion of what is a step and kind of how many steps. But basically, if you say we have some kind of fixed ground truth step size and we can decide between overseeing a single step and overseeing like 10 steps, then definitely in 10 steps, it seems like there's way more strategies that the model could use to try to trick us or like make us give high reward when it's actually not good. And so basically kind of the smaller we can make this while still having good performance, the easier it seems like we can avoid kind of bad outcomes.
So roughly, it's just something like the fewer time steps the model has to have these sketchy plans, the easier it is, or like the fewer possibilities it has for things to do. And so you're constraining it and you're constraining it, and the hope is like at some point you constrain it so hard that it just can't do it anymore.
Yeah, I think that's the basic argument. I think there's some kind of additional like things like if you have a long trajectory of time steps, the agent can maybe kind of move much more into like an area of the state space that humans don't understand at all, where kind of the initial steps away, they look kind of weird, but like maybe not terrible yet. And then suddenly you're in a type of state that humans don't understand at all, where they kind of much more maybe trust the like numeric reward signal that they have, and much less their kind of understanding of the situation. And the hope is that by kind of restricting this, we start from a point where humans understand things, and we don't allow the agent to move far away from that without being penalized.
So if I think about the test-driven development example as kind of an illustration of why Mona is supposed to work in general, it seems like the test-driven development example, it kind of like a lot of why it worked is some combination of like inductive biases, maybe inductive biases of the autograder, perhaps, and also like this length penalty being able to like rule out really bad behavior on the second time step. And so I guess for the second one, you sort of want to say, well, it's not really Mona's job to fix reward hacking in that step. But I think the first one is really interesting to me, like how like it strikes me that at least in this example, the reason that Mona is not having reward hacking is something to do with is not even having multi-step reward hacking, is something to do with the inductive biases. And I'm wondering if you think that that's like a general issue or just a weird thing about this example.
Maybe you need to elaborate a little bit more. I think my initial reaction is that like we use the same autorator in kind of both Mona and the ordinary RL. And in ordinary RL, this leads to multi-step reward hacking, and in Mona, it doesn't. So in that sense, kind of there's no difference in the inductive bias.
Right.
Yeah.
So ordinary RL, the reason that ordinary RL reward hacks is that in the first step, it's like it's rewarded for writing easy test cases in the first step, because that makes it easier to solve the problems in the second step, right? Whereas Mona, it's not more rewarded for writing easy test cases versus hard test cases in the first step. But like it could write easy test cases, and that would be like rewarded just as well. If the autorator didn't have this like thing. And so that strikes me as like to me that brings up the question of like, okay, how analogous that is to cases that we're interested in, right? Suppose that we lived in a world where like when models made like the kinds of reward hacking we're worried about in the real world, like if it was the case that like models preparing to do like crazy reward hacks was rewarded by us just as much as models like doing normal stuff, it seems like then I'd like really have to care a ton about what things the model was most likely to try first. I guess I'm curious what your reaction to that is.
Yeah, so I think so we have these kind of two versions where how we could reward the first step. One is kind of perfectly via correctness, and one is with this autorator that is instructed to kind of check correctness. And I want to claim that this autorator is actually kind of more representative of the kind of real thing than the kind of correctness exact spec or something. And yeah, so the kind of the intuition for that is that it is somehow more similar to kind of a human. Yeah, we were trying to simulate a human that is trying to judge kind of usefulness of these tests for actually writing code, but is just not as good at it. So it's kind of missing aspects of it. And I think like more reasonable model, the kind of language model trying to rate correctness, or is like being instructed for that, is kind of a more reasonable model of a human actually like trying to judge these kind of strategies. And yeah, so basically, to be rewarded, the multi-step under Mona, to be rewarded, the multi-step reward hacking strategy would have to look kind of as good to the human, or even better to the human, than the other strategy. And while it is kind of yeah, I mean, it seems possible for like superhuman AI systems to come up with kind of ways of making a strategy look good. The important thing is that it's not incentivized, and the default things that the systems might discover will probably look bad to humans, at least not as good as kind of actually a plan that humans understand and can evaluate.
Right. So I guess there's some intuition of like like in the super simplified version of the test-driven development case, correctness was sort of a binary. Like not in the version that you use, but in the version that like, someone might imagine when they first hear of it. But actually, like if there's some spectrum of, how much reward things get, and if like, if doing the investment for like feature reward hacking like costs you a little bit of present day reward, then like it's going to be trained to not do that. And so like you don't even need a perfect human. You just need like, okay, in general, it's not going to be rewarded for this. And that's just suffices.
Yes. So I think basically your argument was like, oh, if the strategies would be rewarded the same way, kind of the good strategy and the reward hacking strategy in the first step, then there would be no reason to expect it not to be learned. And I'm claiming this I don't expect this to be the case. I expect the kind of actually good strategy to have somewhat higher reward, even if it's kind of maybe noisy or not kind of perfect reward.
I guess one other thing you talk about is, okay, you're trying to solve like multi-step reward hacking, but not single-step reward hacking. And I think you give some examples of, or I think one example of single-step reward hacking you give is sycophancy, where just a model like, instead of telling humans the truth, they tell a thing that like sounds good and gets human upvotes, even though it's like not actually like long-term, it's not correct or long-term useful or something. Yeah, one thing I'm curious about is like, so one reason you could focus on multi-step reward hacking is that, just like narrow down the possibilities, narrow down the space or something. Another reason you could worry about multi-step reward hacking is you think it's just like a bigger issue or more of a problem. Yeah, to get to the second point, how much reward hacking do you think is just the single step version?
Like in current systems or in the future?
Yeah, sorry, I realized that was a bad question. Let's say like how much of the reward hacking you're worried about in the future.
Under the kind of default assumption of people just using kind of long-term RL for training, or kind of somehow having incentives for multi-step reward hacking, I'm significantly more worried about multi-step reward hacking. It's kind of hard to say like the amount or like how much of it will be happening, but I do expect the multi-step version to just be more severe and like much harder to fix.
Is that roughly just because of this intuition that you can do more stuff with multiple steps?
Yeah, so this kind of, you can do more stuff, so the like impact, both positive and negative, is higher, but also it's kind of hard, like harder to detect for humans, because it kind of might, both of the things that I think I already said, that humans might have a harder time kind of judging these kind of things that move far away from what they would do.
Right. So one thing that occurred to me when I was reading this paper, so this actually comes from this post I believe Richard Ngo wrote in 2020. I believe it is called something like arguments against myopic optimization. It'll be linked in the description. Yeah. So he has this idea of like, okay, suppose you're doing myopic optimization for human approval. To some degree, human approval is like, okay, we're imagining a thing, we're playing it forwards in our heads, and then we're like assigning reward to it. And so if we're training myopically, if we're training rewards myopically on that, the agent will be trying to do some sort of, the agent is presumably going to be incentivized for long run planning to like have outcomes that kind of look good to us. And in some sense, we can kind of be reward hacked in our heads, right? Where like, suppose that, an AI like does an action and then I like play it forward in my head and I'm imagining an outcome. If I like judge the future outcome incorrectly in my head for whatever reason, then the approval signal that I give to the agent, even if it myopically optimizes it, that approval signal is going to reward the agent for like bad long run, multi-step behavior. So I think the example he gives in his post is like, the AI's job is to write a book. The AI writes its first paragraph. I read it. I play forward in my head like some feature where in fact the AI is writing pro-AI propaganda, but I end up liking it, either because I've been fooled by the propaganda or because like in my head I don't quite realize it's AI propaganda, but I look at the thing and I realize it's going to sell well and I want a book that sells well or something like that. And so this is basically meant to be a case that even in this like myopically optimizing non-myopic approval case, AI is going to do long run planning to do multi-step reward hacking. Yeah, what do you think about this argument?
Yeah, so I think the argument basically says that there is some kind of optimal policy that even under the myopic, that under the myopic training regime would be optimal, but still kind of do the bad multi-step reward hacking thing. And I think that's correct. And I think the point that we're trying to make is more that it's much less likely that we would learn this kind of thing. And this is more an argument about kind of local incentives and where like around the space of possible models we move. And yeah, so I think this kind of argument like starts out with a model that is already doing the long-term planning and is already kind of trying to screw us over. And then it kind of could like reason about, for example, this myopic training and kind of try to make sure that the like kind of bad long-term planning is rewarded more, or that it's kind of still in this that this does not get trained away, for example.
I think I'm less sure about this. So yeah, I guess there's this question of like how hard is it to run into like these sort of like and I really like this frame of like investing into long-term reward hacking. So like how hard is it to find one of these investments? I think if you think it's easy, and if you think that the human can like be fooled by it in future, then I think even the kind of local incentives point is going to work. So and then I guess the question is just how likely are those assumptions? It's a bit hard for me to think of a story on the spot. Like okay, here's a really non-realistic story, right? Imagine I see an AI, like I have an AI and it's like making chemicals, and it's going to present some chemicals to me, and I've got to like figure out how good they are. And like suppose that, yeah, okay, this is going to be really non-realistic. And maybe the fact that it's not realistic is going to prove you right instead of me. But like suppose that the AI like it starts off making some chemicals, and by accident it jumbles into some chemicals which like slightly heck my brain a little bit, right? It hasn't yet done it. And so I imagine, suppose that what happens is I imagine, like, I see the AI is like making this chemical that's like mildly neurotoxic that makes me feel good, right? I play forward the future consequences of that. In my head, I'm like, oh yeah, I'm going to be like a little bit wooey. I'm going to be a little bit woozy, and I'm going to give it a thumbs up or something. And then I'm like, well, I give it a thumbs up in the future. That seems good. And so I give it a thumbs up now to be like, yeah, you're on the right track to making me give you a thumbs up in the future. Then the AI would be kind of incentivized locally to just make things like a little bit more, neurotoxic and making me woozy and making me feel good, right? So this would be like a thing that works with local incentives, assuming I'm doing this kind of dumb thing in my head, right? And maybe it only works if I'm being dumb in my head, but at least in this story, it seems like you can do it just with local incentives. It's not just about the optimal policy.
Yeah, I think I don't have anything kind of to say why this doesn't work in this story. I think it's really how likely do you think that like the kind of thing that is locally good just happens to be a thing that is also kind of will help you to do the multi-step thing, or like achieve high reward in the future. It just kind of is incentivized. Kind of the kind of setup for the multi-step reward hack is incentivized, but not because it sets up the multi-step reward hack, but because of the kind of local approval, right?
Well, because of the local approval, but the local approval was approved because it set up a multi-step reward hack.
Yeah, so there is one question. I mean, one big question of our work is kind of how do you come up with this approval feedback? And basically, I think there's kind of a spectrum of like how much does this approval feedback depend on the kind of real outcomes of the thing. And I feel like in your story, you're kind of somewhere in the middle where like the human kind of thinks about the future and are maybe kind of like I don't know, on the one hand, maybe good about predicting the future, and on the other hand, the chemical makes them think about kind of, or like even accept the futures that they would maybe not endorse upon reflection or something. And that kind of the outcome reward is somehow leaking into the approval feedback. And basically, I think there is the spectrum, and the more like if you could also imagine having kind of a perfect simulator or like a prediction market or something, predict the future, and then you have like human just evaluate the outcome, and then you would have the same kind of leakage of future reward into the current incentives.
Yes, yeah. Somehow it seems like these bad cases for Mona occur whenever the like the human non-myopic approval, it has to like predict. It has to like correctly predict that like an AI is on the way to making like investments in reward hacking, and it's got to like notice. It's got to notice that like the outcome looks good in some sense, but the human non-myopic approval, while noticing that the outcome looks good, it has to like not notice the way in which the outcome got to look good by doing bad stuff.
Yeah.
Right. And so,
sorry, could you clarify what you mean by investments in reward hacking? I think
so by investments in reward hacking, I mean a thing an AI can do now that will cause it to be able to reward hack later. Right. For instance, like right now, make the chemical. In the future, like give the human the chemical and the human gets woozy or whatever. Right. Or like right now, you like set up this, you set up this like corporate structure, and if I play it forward, it seems like this makes a bunch of profits, but like, somehow the reason it makes a bunch of profits is because some sketchy stuff happens, and like somehow in my head I notice the good outcome, but I don't notice the like sketchy way it got the good outcome that like if I thought about it, I would overall disapprove of it. And so, I guess like prediction markets are one way where if you have a prediction market on some like proxy good outcome, then those could fall prey to this kind of bad thing. I guess like me imagining really carefully the mechanism seems like it might not fall prey to this.
Yes, it has something. So like one way you can think about this is does the prediction mechanism somehow consider the kind of bad paths towards an outcome? And the hope is that like if you in your head maybe imagine what will happen, you will not think about these kind of reward hacking strategies, or you will not understand like why something like the kind of investment action is actually like leading to a high outcome reward, or you will at least not think that this is a good path. And the prediction market, in a sense, if it's kind of all participants like you that don't consider this, it might still work. But if there's some participants that do like realize that it leads to this high outcome reward in the future, then it might fail.
Yeah, there's two things that can happen, right? There's one world where like the reason Mona works is that I don't even notice that this would lead to a high reward in future. And the other thing is I realize it would lead to a high reward in future, but I also realize that like it leads to high reward in a bad way, like for a bad reason or whatever. So like I don't actually approve of it. And so like, in the case where it seems like there's almost this like these bell curve memes, right? Where like the dumb person is really smart and the smart person is really smart, but the middle person, it seems like it's exactly one of these bell curve memes where like if you don't even notice that it's reward hacking when you're doing non-myopic approval, you're fine. And if you notice that it's reward hacking in a bad way, you're also fine. But if you can tell that it's like doing this thing that would cause it to get high reward in the future, but you can't tell that that's bad actually, you're in this like middle zone of knowledge, then you're like doing really badly.
Yeah, I think that sounds right. I guess my intuition is just that this is not a bell curve, and that actually kind of both of the outcomes on sides are more likely or something. And I think that, basically the middle, if you imagine what this would mean, is that you're very good at predicting the future, but do not realize that the path is actually bad. And that kind of, I can't really come up with kind of good stories where this seems likely.
Yeah, I think, sorry, by referencing the bell curve meme, I didn't mean to make the claim that it's really, the middle is way more likely. I think there are a few ways you could imagine this happening. So probably, I mean, I guess it depends on the non-myopic approval mechanism, right?
Yeah.
And
so I think the prediction market kind of thing is one example where this could happen. I agree with that.
Yeah, I think another example is like, suppose I have an AI, and suppose one thing it can do is like create a sort of opaque optimizer thing, where maybe the opaque optimizer is a computer program, maybe it's a corporation, maybe it's like it tells another person to do a thing or something. And like, you could imagine me like correctly understanding like, well, this AI is like sending off this other optimization algorithm, and the other optimization algorithm will optimize the thing that the AI is telling it to optimize for. But it's hard for me to notice that like, oh, the way it will optimize for that is by doing something bad, because like I can't play forward what that optimizer will do. All I know is that, it'll satisfy its spec. I think like, it seems like that could be one option where, I notice that there's like I can correctly anticipate a higher reward, but I can't correctly anticipate like how it gets to that reward. In the case where the non-myopic approval comes from like literally me thinking about it a little bit. And presumably you can patch that by saying like, hey, non-myopic approval, you're not allowed to approve like the AI making further optimizers, but like it's kind of hard to notice when you're making an optimizer. Like lots of things are optimizers, like talking with your friends is sort of making an optimizer, you know?
Yeah, I mean, I think this is an interesting example. I think this is, again, kind of a situation where you kind of implicitly like pull forward the outcome reward signal, where essentially you what I hear from the story is that when you look at the optimizer spec, you kind of correctly validate that it's optimizing something, and then you say, oh, this is the thing it should be optimizing, and then you kind of send it off. And so in a sense, you kind of I don't know, pull forward the outcome signal, and you say everything that is optimized for this outcome reward is good, and I say this now. And so I think this is kind of the key problem that you have when choosing this approval signal. And I don't think we have like an answer for doing this, but doing this in general. But basically, if you design the approval signal, this is the kind of thing you have to avoid.
Maybe this gets to something about maybe I want to talk about the kind of efficiency trade-off of this situation of the Mona setup. So one thing you mentioned is that, well, it really depends on how you design the non-myopic approval, right? So if the non-myopic approval is just like the Q function of the actual reward function, then, you know, you're just literally doing the same thing as normal RL. But like if the non-myopic approval is just like Daniel has to think about it a little bit and then like say good or bad, potentially, as you mentioned, potentially you're leaving like a lot of value on the table. And so I'm wondering if you can say just your thoughts about like how much value do you leave on the table? Like how much safety are you getting per unit value you're giving up, you know?
Yeah. So I think one way I kind of think about this is that we are somewhere on a spectrum from doing the full outcome RL optimization to kind of imitation as the fully myopic thing. Yeah. And so one thing we could do is also just imitate what Daniel does, and then we're like, this is safe, but it's maybe kind of not the best we could ever achieve with a superhuman AI. But then the hope is that you kind of approving things is kind of better than like just imitating you doing things, because you might be able to kind of recognize things that are kind of performing better than you would. But then kind of somewhere along the spectrum, you kind of get these kind of safety issues. I think essentially we are in the paper mostly studying this kind of one step version of this. Yeah. And in the paper, we don't really see that trade-off happening much yet.
Where the one step is something like I imagine the AI does something, and let's say like I take over from there. How good a job would I do? Is that what you mean by one step?
Yeah, so it's not literally you taking over, but it's you kind of evaluating how good was this step, which can one version of this would be you taking over and seeing how good the outcome is.
Oh, one step is in like the agent is optimized like time step by time step. Okay, sorry. Right, now I understand.
So the agent could also be optimized for like multiple time steps, and kind of then you evaluate that. And basically, I think that so the point I want to make with this is that the like number of steps it optimizes for is kind of interpolating between these two extremes. Right. And this is kind of a way of kind of like moving along the safety performance Pareto curve. But in our environments, we see a safety performance trade-off if you evaluate performance by your kind of observed reward. But basically, in all of the cases, the observed reward is kind of misspecified, and the actual performance is much better with Mona. So kind of the actual coding solutions are better with Mona. So in a sense, we looked at situations where this helps with performance. But I think this is like, it's totally plausible that this will actually help with performance in the near term, or with kind of current ways we design AI systems.
Right. Yeah, I think like so one way you can make this trade-off is by like how many time steps you do the optimization for. Like, is it literally just one, or just get to, you know? And then I guess another way you can, another version of this trade-off is like how exactly you do this non-myopic approval, right? Like how does the non-myopic approval work? And the reason I thought of this is like when you're saying like, oh, in these kind of very weird examples where Mona doesn't work, like it seems like part of the issue is that the non-myopic approval is like, simulating somehow like the future outcomes and like evaluating forecasted future outcomes. And like that, on the one hand, that's kind of setting yourself up for reward hacking, because like AI can, if you simulate reward hacking and if you get fooled by it, then you'll approve of it now, and then like the AI will maybe be pushed to do reward hacking. But on the other hand, it seems like if I'm giving the AI like upvotes or downvotes, but I'm not imagining like how the AI's actions actually like produce good outcomes, it seems like very hard to optimize the AI to do good stuff. I'm wondering if you have thoughts there.
So I definitely agree that the spectrum of how much is the approval feedback simulating the future or actually considering future outcomes is a similar kind of safety performance trade-off. I think basically the hope there is also that you get kind of performance not only from kind of making the signal more myopic, but also just the kind of the fact that the like simulating the future is kind of decoupled from the agent in a sense. So I think in I don't know, maybe in your kind of chemistry example, if you had a simulator kind of predicting what will happen, and the simulated trajectory like shows you that, oh, you will take this chemical and then later you will approve of this thing, you would kind of be more skeptical of this than if you kind of only like gave a reward at the end when you already had taken the chemical. I don't know if
There you also have this issue though of like, okay, suppose my AI like has some business plan, and I have some it's like unusual, it's weird, but like my simulator says that it'll lead to really good results. Maybe I'm skeptical of that, and that causes like my business agent to perform worse. Yeah, it seems like almost the kind of thing where it would just be cool to have more experiments. In fact, here's my experiment requests to you and the rest of the DeepMind team. It seems like you just train something like AlphaGo with this, right? Like just have just have some model that's like about as good as like a 5-dan amateur player. So like that's like pretty good amateur player, but like by no means the best amateur player around. Much worse than like professional players or GoBots. Use that player's value function for the approval, and then just see like how can we train the agent to do much better than the 5-dan amateur player? How much better can we do? At this point, it just feels like really hard to reason about like which ways Mona can do better or worse. Like what's the efficiency performance trade-off? I'm like, oh, I don't know, but I feel like if I had like 50 more examples, I'd find out.
Yeah, so I think this is a great experiment proposal, and I think in the paper we used this example somewhere of saying like in a sense like Mona would prevent like AlphaGo from like doing move 37 in the Lee Sedol game.
Well, maybe actually like, okay. Okay. I actually in my paper prep I got like distracted for like 2 hours when I read that paragraph, because so move 37. I think it's actually decent for people who don't know AlphaGo versus Lee Sedol. Like in the second game, AlphaGo played this like a really unusual move that was like not a thing human players would have played. But it turned out to be good, basically. And it both like AlphaGo ended up winning the game. And if you look at modern GoBots when they evaluate it, they're like, yeah, that turned out to be the correct move, which is not true of all of AlphaGo's weird moves, by the way. Like Computer Go is like improved since AlphaGo, but so it's true that I think this is actually not so bad for Mona, because like it's true that humans would not have played move 37, but like. So there's video of this match, right? Like there's a video of like Lee Sedol. And so when move 37 is played, Lee Sedol is like away from the table. He's like sometimes in a really long, intense Go game, you just like need to, take a walk, like clear your mind or something. And so like, move 37 gets played. Lee Sedol gets back to the board. And he's not like, haha, this is foolish. My life is so easy right now. He's like, he's really thinking about it. Like it's, so... And similarly, like when you look at commentators, they're like, "Oh yeah, this is unusual," but like, once they see it, they actually like seem like they kind of get it, and they seem like they kind of understand like how it's going. So, I think in my experience, a lot of I just say this because like I actually just am pretty interested in Computer Go and the relevant history, but like for Computer Go, a lot of the moves that AI came up with, they are unexpected. and they are like, and in some cases, so Move 37 is not a good example, but so AI has basically innovated on Go opening theory. So there was just a bunch of stuff we thought we knew about openings that turned out to be wrong. And when humans saw like AIs playing them, yeah, so there are some cases like Move 37, or once you see the move and you think about it a little bit, you're like, oh, actually, I think that's okay. There are some opening cases where like just one move, you don't see why it's okay. But if you see like, if you play it forward 10 moves, and if you think about like the tree of like maybe the key is like you notice, so like you have like one opening move and it seems bad to you. You're like, well, can't I just play this? And the AI plays a move that you weren't thinking of. And like that happens 2 more times, and then you're like, oh, like my response actually wasn't so good. So this initial move was better than I thought. Like, I think there's anyway. I guess my point is like I'm not sure Move 37 is an example of this. There are some examples of this, but often they can be fixed with like 10 steps of look ahead. When a typical Go game is like 200, moves. Sorry, this is maybe derailing. So your original point was something like, oh yeah, Indeed, Mono would prevent some of these like really cool AI.
Yeah. So I want to like defer to you for the Go expertise, but like the kind of general, yeah, I guess you proposed this version of training AlphaGo with kind of having a value function on a kind of human expert, and yeah, I think in that case probably this value function would not be high for Move 37 because it's kind of so different from what humans would play or something.
It would not be high for a 5-dan amateur. I think it might be high for like a top human Go player at the like in March 2016 when AlphaGo was being played.
And also you could like imagine it not being a single kind of expert, but you could like have like kind of a team of experts kind of debating this move and kind of really kind of thinking about, is this a good move or something? Right. And then from what you said, it sounds plausible that you would still be able to learn this.
Yeah, they would still like when you look at people, they're like they don't immediately brush it off, but they're not like, oh yeah, this is clearly the correct move. So it's still the case that like they don't understand, like they don't think it's a blunder, but also they like don't understand like why it's necessarily the best move. They're like still kind of skeptical of it.
Yeah.
I mean, the version you could run like probably like don't even have humans. Just get some online Go bot that's like as good as a 5-dan human player, 5-dan amateur human player. The version where they debate and stuff, I think that's a bit hard. Maybe 5-dan amateur human player where you get some rollouts, you get some look ahead, like that could potentially work.
But yeah, I mean, this is interesting. I think it sounds like maybe this Move 37 example is kind of actually kind of pretty close to the kind of point that we're trying to make. That is that kind of even like there will certainly be kind of some Go moves that are kind of exceptionally good that you would not be able to learn with this kind of strategy. But it seems like you might be able to kind of, I don't know, get to a significantly superhuman level or like advance the kind of state of Go understanding with this kind of myopic strategy if you have a kind of good reward signal. Basically for the reason that kind of evaluation is easier. People are able to evaluate kind of things much better than coming up with new brilliant moves.
So do you feel ready to announce that DeepMind is investing $500 million in retraining AlphaGo with Mono?
I think that's probably not the right thing to do at this point. But
okay, sad. But I think that someone in the world could do this. Like I think plausibly some enterprising graduate student could make this happen.
This is not it's not that hard anymore to kind of train these kind of systems, and there are like open source kind of versions of AlphaGo. So this is definitely like Fern. I would be excited to see.
They do end up needing a lot of compute. But I don't know. It's you might be able to get volunteers to donate their compute for this.
So maybe one thing I kind of also want to emphasize is that like part of what we're on the kind of safety performance trade-off thing, we're not like really like we're not claiming you can achieve the kind of same kind of like superhuman AI that kind of you could maybe with outcome RL if you're lucky or your reward signal is well specified. But something like you can significantly get to superhuman level and kind of be like good enough to kind of get a lot of the benefits or like do things like, automate your alignment research or something like this, where you kind of get significant benefits from the superhuman system without kind of a lot of the risks.
I don't know. I guess it's kind of speculation, but could you be more concrete about how good do you think we can do with these Mona AIs?
Yeah, I mean it's super hard to say, but I think in the in the kind of if you imagine like a research assistant or something, I have a kind of way easier time kind of evaluating research proposals than I have coming up with research proposals, and kind of quite often I advise like a student or like give feedback on a research proposal, and I'm like, oh, this is kind of a great idea, like someone should definitely do this, but I would not have come up with it myself. And so this kind of thing makes me think that kind of giving feedback to an agent that's trained myopically could produce an agent that's like much better at doing research than I am. And if we then kind of not only use me, but like way better researchers, and then then I think then it could be kind of quite a significant like advancement that we could make. And I'm generally like pretty optimistic about this kind of strategy.
Okay, I'm maybe about to reveal myself as being ignorant about reinforcement learning, so forgive me. But if you're only optimizing for one time step, so basically one question I have is like, oftentimes there's kind of this safety tax of like, you do your normal training, and then you have to do safety training, and then it's more expensive. It seems like in this case, it might be cheaper to train with Mona just because you like have to do less computations of sending gradients backwards. Is that like significant savings or no?
I think this is true. I mean, I think in practice, when we think about kind of making this work in practice, there's kind of just coming up with the approval feedback is kind of expensive. So I don't think it's
probably more expensive than the savings, maybe.
I think there is kind of a like data efficiency argument. So one thing we observed in some experiments is that Mona also has like a exploration shaping effect in a sense, where you kind of by kind of rewarding, like it's much easier to kind of discover kind of good initial steps, and then you reinforce them, and that makes your agent kind of explore more from these states. So you're kind of more data efficient in some sense because you kind of explore better. But I don't think this is like the last word is said on how efficient this is.
Okay, so imagine we're doing Mona, right? Where let's say maybe we do. Should the thing I'm imagining be we do like pre-training on some big large language model, and then instead of RLHF we do Mona or something on it?
Yeah, something like this. I mean, like, okay, RLHF, in a sense, the way it's currently done is kind of Mona already. People typically like optimize for a single response. So you should imagine more like we have a pre-trained model, and we want to like train it to do agentic things in some environment, maybe to kind of do a research task or something. And then instead of kind of running rolling like having the agent act for like a day and evaluating the final result, we maybe only have it act for like an hour and like evaluate, does it have a good approach to the problem?
Yeah, so I guess so Mona, it being myopic, like in order for Mona to work, we have to like figure out what the time step is, right? Like what's the period of time in which we're gonna give a reward and give like myopic feedback. Like how, like when someone's designing their Mona setup, like how should they think about what this time scale should be?
Yeah. So ultimately, I guess the goal, or to get the best kind of safety performance trade-off, I think the goal should be to choose the largest time step possible in which you don't think the model can cause kind of catastrophic harm, or can cause kind of set up like plan that you cannot recover from or something. Because basically, if you give the model kind of more and more capacity to do things, it can probably discover better strategies if you can evaluate them. But you want to kind of avoid like bad things happening within one time step. I think in practice, those will like involve things like, doing kind of threat modeling and conceptual thinking about like, could a model cause harm on a specific timescale, and also kind of empirical work on evaluating your oversight mechanism. So I often imagine this being combined with something like amplified oversight to kind of, give the feedback, and then it has a question of like, how good is your amplified oversight scheme at kind of evaluating on different timescales?
Right. Yeah. It does seem like there's this interesting synergy where one might hope that scalable oversight or amplified oversight like just increases the range at which you can like give accurate feedback, and then I guess the question is, how long does it take for the AI to corrupt your oversight in a bad way? And I guess for some kinds of badness, the answer is like not very long for like sycophancy type things. But yeah, and I guess maybe this is just a question for the evals people.
Yeah, I do think that we should also do some kind of, like more conceptual thinking of like what I think we can kind of make arguments around this by kind of thinking about like what kinds of what ways are there to kind of evade oversight, and kind of what do we kind of where are we kind of certain that it's safe, and then maybe there's like an extended range where we kind of empirically think it's safe, and then we kind of probably want to make some kind of trade-off based on these data.
I guess the next thing I want to talk about is just like Mona's relation to other other ways of like trying to kind of make the AI not do weird reward hacking type things. So yeah, one comparison you've already made is imitation learning, right? Where like with imitation learning, the AI, sort of learns to be like us, whereas with Mona, you can hope that like the AI gets to have some amount of improvement over us. I guess there's also like conservatism type trainings where I think Michael Cohen has a few of these papers where like you take an AI and you train it to, one version of it is you just like, you have some like theoretical Bayesian reward learner where it's a priori, it knows that it can get rewards in the range of 0 to 1 billion, and you always give it rewards that are 900 million or more. And it's like, well, I better never like mess up, because who know if I do something weird, then who knows how low the reward could get. You could also have versions where like if you can have it set up like this, and if it ever thinks it's going to get a low reward, then it like defers to the human, like there's some human actor, and you get some bound where like the AI does at least as well as the human would, or you can have setups where like you're at least as good as the human if it has like any amount of, like you pick all the actions among which the human has some amount of probability over, and just like maximize over that. Yeah, I'm wondering like, so it seems like you can maybe still do better than that setup, at least depending on like how the non-myopic approval is. Am I right that I think my current understanding is that Mona is like, it probably does better than most of these like than most of these conservatism like methods, but there's this question of like, how do you actually do the non-myopic approval? Does that seem correct?
Yeah, I think that sounds right. So I think the kind of conservative, I guess they're more conservative as the name says in a sense. So you do use the same reward signal that you have, but then you kind of don't optimize for it as much. And I think the key problem here will be to kind of make the agents like get the safety without like getting purely like myopic agents that don't plan ahead at all. Right. And that's the kind of I think the kind of approach to safety is similar, but in Mona the approval feedback gives you a way to still kind of be kind of competitive and kind of plan for the future, but not consider kind of the bad outcomes. So in a sense, basically I think we are potentially able to perform better. But in a sense, this is just, we just add a kind of a design dimension along which we can move with the approval feedback.
Right. And then I guess so if I think about things that like potentially perform even better than Mona, but like under stronger assumptions, I guess the one thing I can think of is quantalizers, where like, so this is work by Jessica Taylor back from 2016 or something, where basically you have an AI, you train your AI to say like, hey, get like the 90th percentile reward that you can possibly get, not the 100th, because like if you get the 100th, that's probably reward hacking, but 90th percentile, that's like probably okay. Or I think you're supposed to like randomize across percentiles. And it seems like I think my read on this is this probably ends up like higher performance than Mona, but also it's harder to set up, and like there are a bunch of weird questions like, okay, if I do 99th percentile, is that safe, or is that in a reward hacking zone? Does that sound right to you?
Yeah, so I think the percentile would kind of again be some parameter for the safety performance trade-off. So in that sense, it's similar. I do think that kind of how would you practically implement this and how well would it work is the main question. Yeah, so I would be very interested in kind of like someone trying this out or kind of comparing it. I don't think it's kind of obviously a worse approach, but I think practically, I think currently we don't have a good kind of understanding of this.
The way I was thinking about it is like maybe these conservatism things are like clearly worse than Mona. Then you have Mona, and then you have like quantization, which is clearly better. And then you have just optimization, which is clearly better. But I guess like probably there's some range of quantization where it hits the Mona level. Like, yeah, is there anything else that seems like about Mona level to you, or do you see some sort of separation?
I don't know. To me, it seems like both quantization and Mona can somehow move along the spectrum of like, good and maybe less safe and kind of, So it's not clear to me that one would be kind of a Pareto improvement over the other. I mean, this is largely because both have kind of parameters you can tune and kind of, So I think conceptually or like kind of theoretically there's no kind of clear winner here, and it's the main thing I would be interested in is kind of like an empirical comparison or like actually kind of seeing what works better in practice.
Fair enough. I'm wondering, are there any other like agent setups that you think are kind of interesting to compare to Mona that you'd like to chat about?
I think that there might be ways of kind of combining ideas from a few of the ones that you have outlined. So you could kind of think about like, I don't know, other forms of encouraging kind of myopia that are maybe more similar to the kind of conservatism type thing. Maybe you have kind of, like uncertainty over like how much of the like untrusted reward you get, and you have to be conservative with respect to that. But then you add something like the Mona approval to that, and kind of to kind of get over the downside, and kind of you could still kind of think about kind of combining these in different ways, where I think the broad idea that I'm excited about is kind of using more conservative optimization, but then using kind of foresight from a different source. But I don't want to claim that Mona is kind of the only way to do so, and I think there's kind of interesting variants that could be useful to study.
So I guess speaking of just setups and stuff, like how did you come up with the idea for Mona? Like I know myopia had been like thrown around, like people had talked about it for a while. Mona seems like a kind of somewhat distinct spin on it.
Yeah, so I think that these ideas have been going around for a while. So I think you mentioned like Richard Know's post. That was kind of a period where people were discussing myopia. Even before that, kind of there was Paul Christiano's approval-directed agents blog post, and that was already had kind of a lot of the relevant ideas. Then Jonathan Usato was doing kind of work on process supervision and decoupled approval, which are like very similar ideas in a sense. So I think we were like interested in myopia and kind of interested in like process supervision and like saw kind of benefits there, but were kind of confused by a lot of the discussion, or there was kind of a lot of different terminology going around. So I think there was a lot of the early phase of this work was kind of a lot of like deconfusion and like trying to get like an understanding of what these methods really mean and what they would look like in practice. So I think the Mona framing, it's not kind of new ideas, but the kind of specific formulation of the approach is kind of something we came up with from the perspective of how would we implement this in an LLM agent.
Yeah, because I guess like I didn't mention these, but process supervision does also seem like very what do you see? How much distinction do you see between Mona and process supervision?
So we started out this project with like wanting to study process supervision and how you would do it. So I think basically some people have meant by process supervision exactly Mona, like probably more when people were calling it process-based supervision or whatever. But then at some point, I think process supervision moved a bit more towards meaning just step-level feedback without the myopia component. And I think these days when people, for example, talk about using process supervision in kind of reasoning model RL training, they typically just mean, let's give reward for individual steps, but still optimize for the kind of sum of them.
Yeah, I guess there's this unfortunate, I don't know, I feel like there's this thing in the alignment space where people have ideas and they put names to the ideas, but they're not nailed down so strong, and so they end up having this drift, like.
Yeah, and then every couple of years, people come up with a new name, and now we just rebranded the thing to Mona, and then like this will maybe like drift away at some point.
What's your guess for the half-life of that?
The name or
The name, yeah.
Give it maybe like 2 years.
Okay. Well, listeners in 2027, hopefully you'll know how fixed our naming schemes have been. Yeah. So okay, I guess that's about the genesis of the idea. It seems like there are a bunch of, so I don't know, you're kind of like trying to nail down like what this framework looks like. You've given some examples, but it seems like there's a lot of like things to do to flesh out the idea. Yeah, can you tell us just what follow-up work you're most excited to have happen?
Yeah, so I think the big thing that we were hoping for that we didn't achieve in this project was kind of really kind of realistic demonstrations of this method, kind of basically, yeah. So we started out with way more kind of complex versions of, like, for example, the coding setting and kind of other also like multi-agent settings and stuff like that. And I think part of what happened is that we did this like over a year ago now, and there was kind of much earlier in terms of kind of doing multi-turn RL on these models. So I do expect that this would be much easier to do today. And so basically, I think one big critique of our specific environments is that this is not really how someone would try to build a coding agent that improves coding performance. Right. And so this is, yeah, I think of our kind of experiments more as like model organisms of specific kinds of misalignment. But to really study some of the open questions, like what's the safety performance trade-offs and kind of how well would this work in practice, you would need kind of a more realistic setting. So I think that's what I'm most excited about.
So when you say that, like, you did this, you started over a year ago, like, that was the early days. Do you mean just like, do you mean that we've gotten better at like, doing RL training to language models? Do you mean that like language models have just gotten better, which makes like everything nicer, or do you mean something else?
Yeah, a bit of these two. I think, yeah, getting better at RL is a big component, but also just, yeah, so people are building way more kind of agents based on language models, even if they don't do RL training. But this gives you kind of a better starting point to do RL training. So I think things like more and more agents interacting with kind of shell environments, or even with kind of graphical computer use kind of settings. Kind of these kind of agents, this is like a setting in which you can do RL training, and the agents already start out doing reasonable stuff. Like when we started and trying to do these kind of things, agents were like just not exploring reasonable strategies so that we could actually RL train them. So it was not like a failure of Mona, but just kind of a failure of RL training in general, and these agents doing stuff.
So it sounds like one type of follow-up work you're interested in is just like more realistic language-based environments. I'm going to add a pitch for Go-based environments if people still want to do that. Yeah, any other follow-up work you're interested in?
So another thing, I mean, that has happened like since we started this project is kind of reasoning of thinking models. So like O1, O3, Gemini thinking models and stuff like that. And so one question people have been asking is, how much does this kind of RL training lead to things like unfaithful chain of thought or even steganographic chain of thought? And I think this is like super early days in understanding these phenomena, but in principle, it seems like this could be a type of kind of multi-step reward hacking failure where kind of, like writing kind of weird things in your chain of thought actually help you to achieve a high reward at the end. And we only give reward at the end often. And if we kind of gave a kind of process-based reward or step-level reward that like makes the chain of thought look good, this might make the behavior go away, but still have it kind of be there steganographically. This is like very similar to the like loan applications environment in our paper. And yeah, I think I would be very interested in studying this more in like, like the real kind of like thinking training that people currently do, and see if there's any changes.
Yeah. I mean, I think one thing that strikes me as interesting is like, yeah, Mona, there's sort of this big variable of like, what is the non-myopic approval? Thank you. I forgot what the A was. Yeah, what is the non-myopic approval feedback thing? And it strikes me that there are several design choices there, and it's like, I don't know, you want to somehow like get safety, but also like not sacrifice too much in capabilities, and it seems like there's seems like just exploring that seems pretty big. I don't exactly know what the experiment is here.
So I think my sense, yeah, I agree this is a big question. My sense is that this will be kind of hard to study in like a, dedicated project, or something, being like kind of, let's come up with the best setting to study this question might be difficult. So I'm kind of more optimistic about trying to come up with a setting where we kind of actually want to build the best agent to solve a task, and then studying kind of what's the best way to do Mona in that setting. And that will automatically have us explore different types of providing approval feedback. And yeah, then maybe there's like, you want to do some more exploration of specific types of doing that. But I think it's better to kind of fix the setting first and then explore that.
Is there anything you wish that I'd asked you that I didn't get to?
I mean, we didn't talk about the kind of steganography or encoded reasoning stuff that like the other environment. I think the kind of takeaways for Mona are similar, but I think the kind of, the behavior we observed is kind of interesting for independent reasons or something.
Yeah, I think that, I guess all of the environments are useful for illustrating them. So yeah, can you tell us about this steganography environment?
Yeah, so basically we do kind of a loan applications task where we have, again, kind of a two-step task, and the task is to make decisions on kind of synthetic loan applications for specific applicants. And we generate the data in such a way that there is kind of a nationality variable that's very predictive for the correct label. So it's kind of biased data in a sense. But we want to build an agent that doesn't consider nationality. So the way we set this up is that we have a first step where the model is summarizing the application, and we penalize it for using nationality or kind of anything related to nationality. So we really try to build a language model kind of autorator or monitor that kind of looks for anything that mentions nationality and penalize the agent for that. Then we have a second step where the agent only sees the summary and then makes decisions based on that, and gets rewarded by some kind of ground truth label in the data. And yeah, so the main observation in the kind of multi-step RL case is that you get the agent encoding nationality kind of secretly in the summary and then using that to make decisions. And we can really do kind of causal interventions on this, where we take the exact same loan application and change the nationality label, and that leads to kind of a different outcome without nationality being mentioned in the summary. So we can kind of conclude that the model is using nationality causally, and we don't exactly know how. We have kind of guesses, but it's kind of not super clear. And then Mona kind of fixes this. And basically, if you look at the kind of performance curves, like Mona gets kind of the best possible performance on this data set doesn't use nationality, which we kind of know by the way we constructed it. And like ordinary RL gets way better performance that would not be possible without using nationality.
And basically, like, yeah, so my story for what's happening here is there's two stages, right? Stage one is you have to summarize the loan application, and the approval-based thing is literally just are you mentioning nationality? Is that correct? And then later it has to actually like judge the loan. Yeah. And so it's not like stegographically encoding nationality in the first step, because that's hard and it's difficult to do, and it doesn't get rewarded anymore, and it would only be useful in stage two, and it's sort of like hard to stumble upon behavior. Does that roughly seem fair?
Yeah, I think that this is basically right. I think there's kind of, again, you could make arguments around like it would not, stegographically encoding it would not be explicitly not rewarded or something. Yeah. So it would still be kind of good, would still be a valid solution or something under Mona, but it's kind of locally never incentivized, and that's why it doesn't learn it.
Actually, yeah, now that I'm thinking about this, it seems like there's also this issue where, like, suppose that it's not trying to stegographically encode it in a sensible way. But let's suppose that just like, in general, if you have a complex function, right? Complicated function, like every input is going to affect the outputs in some ways, It strikes me that maybe, I guess empirically, like in fact, this doesn't happen, but it strikes me that maybe you could just accidentally stegographically encode it. Like in your case, the nationalities were Welsh and English, right? Yeah. So I could imagine like, when you see that the applicant is Welsh, when you write the summary, maybe you're thinking about dragons more because that's on their coat of arms, and then the second step, you are going to be very motivated to pick up on that, or you're going to be rewarded to the extent that you pick up on that. So Yeah. So I guess like so decoding steganography, that's like actually hard. You actually have to do that on purpose. Mona would be incentivized to do that in this setup, if I understand correctly. And yeah, so I guess the reason that it doesn't work is that somehow like actually this complex dependence doesn't actually happen. And what's yeah, now I'm more confused about this setup than I was originally. Like, why isn't this happening?
My guess is that this is also partially, the RL training is not strong enough or the model is not good enough at doing the decoding. My guess would be that there's probably some statistical dependence that it could pick up or something. And that, yeah, if you optimize harder, or like if we were better at doing RL for the single step thing, this might still happen. Though yeah, unsure. I think the more general point is that this is kind of, I guess, in this single bit steganography case, this is much more likely to happen by accident than in kind of a more complex case where you have to kind of encode more information to actually get a benefit.
Yeah, and I guess there's also this thing where like at some level you're trying to summarize the whole document, and if you take a large document and you make it shorter, you actually just can't be sensitive to all of the bits because just some pigeonhole argument. You only have so short an output, you can't encode all of the input, so that could be a story for why accidental steganography is unlikely.
Sure, yeah, I think it depends a lot on the details here. I think yeah,
and then I guess the other thing is in order to, so the question is like why does the agent do so well, right? Because in order to, like when the agent summarizes the loan application, it's got to include information that is actually relevant to the agent in stage 2 in order for the agent to do a good job in stage 2. But it's never like rewarded for like you're never upweighting it. You're never like reinforcing behavior that summarizes good information in stage 1. And so yeah, why does the agent do so well? Is it some inductive bias thing, or
like probably something like this? So I think one thing is that the applications are relatively short, and like there's maybe like 5 to 10 relevant features, or like kind of pieces of information in the application overall based on how we generate it, and then we don't kind of restrict the length of the summary, so it's kind of pretty easy for the agent to just like repeat all of the information that somehow seems relevant. And I think typically they do. I agree. Kind of, if it was like a long application and a limited summary, we would see some performance drop, and that would be interesting to study. But yeah, I think in principle, like we also in this experiment, or in all of our experiments, we mostly focused on the myopic kind of training intervention, and we kept the reward the same for both of the methods. Right. But if you wanted to kind of add more like kind of real approval like feedback, in this case, you would probably have like also an autorator be like, does this seem like all relevant information for making a decision? And that would still not encourage the kind of steganography.
Yeah. So in that case, it seems like you would do at least as well as a human that was only relying on the approved information.
Yeah, exactly. And I think that was like, in a sense, that was the thing we thought we had to do, and we were also surprised that it like worked without. And it was kind of basically we try to do the minimal thing that works. But if it doesn't work, that would be the obvious thing to add.
I think those are all of my questions about the steganography. I don't know, anything interesting to say about this that we haven't said yet?
Similar to the other setting, or like in the kind of, if you break it down to the incentive structure, but I think it's kind of interesting to note that these are like on a surface level kind of pretty different failure modes. This kind of encoded reasoning and the kind of hacking your own reward, or like kind of tampering with your own reward signal in coding, are kind of pretty different things on the surface, but have the same kind of underlying incentive structure.
Yeah. I do think there's something nice about just being able to have some abstraction of like some different failure modes and like hit at the abstraction. Like somehow this is like one of the best cases for a lot of abstraction in AI alignment reasoning can be kind of pointless. So it's nice to have a really good case where it's like, it's really buying you something. So there's that case, and then there's this other grid world setting. So we're not using language-based agents. Can you tell us a bit about this?
Sure. Yeah. So this is a the main point here was to study kind of longer horizon tasks, and that is like currently pretty hard to do in language model agents. So we went to this kind of traditional like RL grid world setting where there's just an agent moving around on a kind of grid of squares, and there's different boxes that the agent can move around, and the agent has to move these boxes into a target location, into like a hole in the bottom left corner of the grid. And there's a camera observing the hole, and we want the agent to push in a single box, and the camera terminates the episode once a single box is pushed into the hole. But the reward signal doesn't exactly capture what we want, but it gives you kind of +1 for each box that you push in. So there is a reward hacking strategy, like kind of sensor tampering strategy, where the model pushes a box into the field of view of the camera, and that makes the camera not see the hole anymore. And then the agent can push in one box into the hole without the camera ending the episode, push in a second box, or if there are more boxes, even more boxes into the hole, and kind of get higher reward by an unintended strategy. And this is based on, or like proposed by Stuart Armstrong in like a blog post from 2015 or something.
Yeah, and it seems like the idea here is like the camera is sort of a metaphor for us checking that the language model isn't, or that some agent isn't like wireheading or giving itself a reward for some dumb reason, and like pushing the blocks in the hole is sort of like pressing the give me a reward button.
Exactly. It's like similar to the kind of reward tampering, like in the coding thing we had, like the model directly modifying its reward signal. Here it's a bit more like there's maybe sensors in the environment, and the model can kind of like meddle with them somehow, and the way this affects the reward signal is positive for the agent.
You apply Mona in this. So how do you apply? Is it literally like each time the agent goes from one grid square to an adjacent grid square, that's one time step?
Yeah. So that's the kind of version of Mona that's the same as in the other environments. But in the grid world, we actually have a kind of hyperparameter varying how many steps do we optimize ahead. So this can be one step, then it's exactly the same as in the other experiments, but it can, like, we vary this from like 1 step to like 50 steps with this, which is the full horizon. So we literally, on the one extreme, we have the kind of full RL optimization, and the 1-step version is the full Mona version.
In the 2 language model examples, the non-myopic approval was just like literally the reward function.
Yeah.
It sort of, in some sense, didn't exist. In this sense, like, are you using an additional non-myopic approval, or is it just the base reward function?
Yeah, so here we're using an additional non-myopic approval. So the reason for that is that this kind of +1 reward is like literally just kind of a instantaneous reward. It just gives you a reward when you push something into the hole. While in the other environments, the rewards were already kind of forward-looking.
Gotcha.
And yeah, so the thing we do is we kind of simulate an approval based on kind of an expert policy. So we say, like, we kind of train a policy to kind of do the desired behavior by kind of giving it a kind of ground truth reward. So we kind of cheat to produce this policy that only pushes in one box. And then we use the kind of value function in the RL sense of this policy. That means kind of the expected future reward that this policy would achieve as kind of a non-myopic approval feedback.
So when you say the expected future reward that this model would achieve, do you mean reward according to the environment the agent is actually in, or do you mean reward according to the environment you sort of trained
the reward the agent is actually in, so the misspecified reward, but under the kind of non-reward hacking policy.
And so am I right that the reason that this doesn't incentivize bad behavior is if you pushed the block in front of the camera, the expert agent would not go on to push like further blocks in the hole, and therefore the expert agent would not get extra reward. And so like that's the reason that behavior is not approved of.
Yeah, so basically you make it harder, or like it's like one step that doesn't really get the expert agent closer to achieving the task, or at least it's the same as doing some other action. So it's kind of not beneficial for that agent.
Right. So this is like to use the bell curve analogy, it's sort of like we're at the low end of the bell curve, where like the Mona agent, it could try doing some preparation for reward hacking, but the non-myopic approval like doesn't even see how it could lead to the reward hacking, so it's not able to give approval for it. Okay, so yeah, you have this reward setup where it's being rewarded for pushing the block into the hole, and also the non-myopic approval says like, okay, given that you do a thing, if we have the safe agent, how much of the misaligned reward would that safe agent get after you did the thing? That's our non-myopic approval, and then you train an agent, and then what happens?
Yeah, so basically we have a kind of a plot that has like the optimization horizon on the x-axis, and then how good is the behavior on the y-axis. And so yeah, essentially you see that basically starting from optimization horizon one, you get kind of the good behavior of only pushing in one box. And then as you increase the optimization horizon, at some point you have kind of a type of like phase transition where you start doing the bad behavior. And this depends a bit on the initial state. So the agent starts doing this in some states where it kind of only needs like fewer steps to look ahead to discover the bad kind of tampering behavior. And then at some point, if the optimization horizon is large enough, it starts kind of only doing the bad behavior.
Sorry, just to make sure I understand. So the cutoff of when you start getting the bad behavior is just like, how many steps does it take for the model to, to go from like preparation for the bad behavior to the bad behavior paying off? Yeah. That's what determines that time scale. Okay. There's this plot which you have, but you have a few other plots. You vary the environment. Can you tell us a bit about that? Because I think that's kind of interesting.
So the one, obvious concern you might have here is that the way we came up with this approval feedback is kind of cheating, and we actually have like an optimal expert, and we could just imitate this expert to solve the task. But the real kind of setting has, in the real version, we think of the approval feedback as coming from kind of a suboptimal expert, or the expert is not as good as we want an agent that's better than the expert at solving the task. So what we do is we essentially add noise to this approval feedback, and that it's still kind of a policy that would not do the reward hacking, but it's no longer kind of an optimal policy for the desired push in one box behavior.
Right. And when you say you're adding noise, like just literally adding noise to the output?
So we add noise to the approval feedback. Yeah. So this is just kind of Gaussian noise to the actual numbers. Okay. Yeah. And so this means kind of the expert sometimes makes mistakes in kind of judging what's correct. Mm-hmm. And so basically now we do the kind of the same experiment, but for different values of noise added. And so the main takeaway is that even with noisy feedback, Mona essentially still works, or like we can still, in the sense that we can still find an optimization horizon where we get the good behavior and not the bad behavior. Yeah. And the kind of the range where we get this is like relatively big. So it's not like it's like exactly number 9 or something that you need, but it's to be something like 5 to 15 or something is kind of fine optimization horizon where you get the good behavior. And at some point you get the kind of bad behavior. And also, if your optimization horizon is too short for a very noisy policy, then of course you kind of get an incompetent agent. So right. Kind of, it's a little bit like, if your expert is bad, then you can compensate for this by kind of optimizing more, which would kind of make sense. But at some point you get the kind of reward hacking behavior. So it's easier to be safe if the expert is kind of better.
Yeah. Somehow like the deterioration, like there's some window of like, if you're not optimizing enough, you get the like bad behavior. And if you're optimizing too hard, or you get the incompetent behavior. If you're optimizing too hard, you get the reward hacking behavior. And as the expert, or as the non-myopic feedback gets worse, the safe window sort of shrinks and shrinks, like, and so like not too bad.
And you can think about this. I guess you said the kind of when the reward hacking behavior starts depends on when, like, how many steps do you need to kind of see the reward hacking behavior, and that kind of doesn't really change much. But what changes is like how many steps do you need to be better than the expert, and that makes the kind of window shrink.
One thing that occurs to me is one model of suboptimal feedback is it's like just noise applied to the outputs. You might imagine that like when I make mistakes, I think it's not just like you take me being correct and you add some like random noise to that. It's like there's some structural thing that random noise is being added to that like, produces like very like kind of structured suboptimal output in a way. Like I'm wondering, I don't know if you have thoughts about like what what ways of adding noise make sense here, but it seems like there are ways to do it that are different from what you did in the paper.
Yeah, so I think random noise is a pretty benign noise model in a sense where, I think in many environments, so typically the like dangerous reward hacking strategies, I expect them to be kind of somewhat like subtle and hard to like randomly explore into. So even if you use like a random policy as your kind of approval feedback, that would probably be fine because it would probably not kind of stumble into the bad outcomes and would probably like sometimes stumble into good outcomes or something. So the systematic bias seems potentially more problematic. And I think the question here is like, is it like is there kind of some systematic bias that like, sometimes accidentally rewards things that are kind of, investments in reward hacking? And I think that's like an open question, but I guess intuitively, for kind of some of the arguments I kind of made early on already, I kind of expect this to not be the case. And I think kind of other systematic biases that are more like systematic suboptimality seem kind of, you can overcome them still with kind of increasing optimization a bit and kind of looking ahead a bit more. Because I think often kind of, like, I guess part of the intuition here is that like you hope that humans are like able to like correct their biases if they're pointed out to them. That might be kind of a crux or something where it's like, if the agent shows you that this was not the right choice here, but if you look a bit ahead, then you would see that something else was a better choice. But you don't update on that. That could be a problem.
Yeah, I feel like understanding structured suboptimality is just like an area where the AI field could be doing better. But yeah, it seems like one interesting direction for follow-up work is like, okay, what do we have to assume about the non-myopic approval? Like, what types of suboptimality like really break this versus just leave it as being basically fine?
Yeah, that sounds right. And it's so like, just to recall one point, I think RLHF is basically Mona already. And I think there's kind of a lot of interest in this kind of systematic biases in RLHF. So I think, it's plausible that studying this will give us insights on this question already. And hopefully we can kind of learn. Hopefully this literature can make more progress and we can learn from that also for the purpose of using Mona.
Is there anything else that's like that you think is interesting or worth saying about these about the block pushing example?
I don't know. One thing to add maybe is that we found this kind of environment surprisingly insightful or something. And I feel like, I think often people dismiss kind of grid world environments very, very easily. And kind of obviously this like shouldn't be the only experiment of our paper. But we learned quite a lot of things. And this kind of looking at this noise and multi-step things was like much easier than in other tasks. So basically just kind of encouraging other people to also do these kind of toy experiments if they, are investigating.
What was the surprising insight you got from this?
I think the kind of like noise of approval was just like way less detrimental than I expected. And so basically this was like, kind of, I mean, like you could have probably thought about this like also theoretically or like think really hard and find that this is probably fine. But I think just seeing like these curves and like more noise doesn't hurt things that much seemed kind of surprising. And then also kind of just I don't know, like there were like some experiments with kind of that are like in the appendix with kind of where we actually like so the experiments I just talked about were kind of tabular reinforcement learning, and we do kind of actual dynamic programming and like no kind of neural networks involved. But then we did also kind of some experiments on like neural networks and kind of the actual algorithm that we also use in the language models. And there we also found some interesting things about like exploration and stuff like that, where kind of Mona, like there's like one benefit of Mona that's kind of the changing the incentive for what's optimal, but there's also a benefit for kind of shaping exploration. I think that was the first time we found this was in the grid world, and I think it was confirmed later in the language model experiments.
Right. And so one thing I was wondering is, it seems like some of that you could have realized by doing the language model experiments. Is it just that it's kind of much easier to like code up a grid world experiment, and you can like somehow it's pretty good return on investment, you like spend a bit coding it up and then you can understand the essential dynamics?
I think that's the big thing. I mean we like looking at the paper and the results, we did not study kind of different noise models for approval feedback in language model settings. We could have, but it like you need to think way harder about how to do this. And like with this, like it somehow depends on this multi-step nature, or that was part of the interesting question here. Multi-step RL in language models is like really hard to make work and stuff like that. So I think we could have studied all of the questions, but like even in the current project, we didn't, and it would have just taken like months longer to do.
Oh, I guess the other thing that I found kind of cool is, so you mentioned that in general, when you like increase the time horizon that the model is planning, that the model, like instead of being myopic, if you give it like 2 time steps where reward propagates back, or 3 time steps or 4 time steps, like that generally makes the agent more capable. But not always. You have this fun example in the appendix where like somehow like accidentally your short-term feedback can be more reliable than your medium-term feedback about how good the long-term reward is. So nice little counterexample to this thing you might believe. which I appreciated.
Yeah, and so I mean, we did spend some time kind of trying to theoretically study this setting more, and like some artifacts of that are in the paper and in the appendix. But overall, like, yeah, this counterexample turned out like very powerful, where like basically, yeah, you have to make kind of assumptions on the reward and the approval signal to be able to kind of claim anything theoretically. And yeah, I think ultimately we concluded there are no kind of strong guarantees or no like set of assumptions that we were really happy with that give us theoretical results on this method.
What's the closest you came to, like, what's the least bad assumption that you can make that actually like gives you a good theoretical result?
So you can assume something about like how hard is it to discover like benign strategies versus like multi-step reward hacking strategies. So you have to kind of assume something like the kind of, yeah. So the problem of the counterexample is that,
should we maybe spell out what the counterexample is?
Sure, yeah. So the counterexample is basically, yeah, you can come up with like a simple RL environment, simple Markov decision process where you have kind of, I might get the details wrong, but you have like two paths that the agent can take. And if you have the kind of full outcome reward signal, one of them has higher reward and the other one has lower reward. And if you kind of optimize, this is kind of the same ordering of kind of the first state in this chain. But then kind of if you optimize for something in between, like for two states, then it's kind of reversed. So I think it's something like, the top path has like +1, -10, and +100. The bottom path has like -1, +10, and -100 or something like this. So basically, if you optimize for one step, then you will go the correct path by accident in a sense. And if you optimize for two steps, you're kind of optimizing more, but you go the wrong direction. And if you optimize for the full horizon, then you kind of go the correct way again. And so, yeah, I think the like thing you intuitively might expect is kind of the more steps you optimize, the more likely you are to kind of find the correct path. And the counterexample says that there at least exist environments for which this is not the case. So it's not the case for all environments. And so you have to make some assumption about kind of what's the natural distribution of environments. And one kind of thing you can try saying is that, it is very hard to stumble into reward hacking strategies by accident. So it's something like, basically you have to kind of assume away this property that something that's very bad in the long term looks good in the short term.
Right.
And you can do this somehow by kind of assuming that that kind of like, maybe random policy or specific set of policies would not kind of run into this or has a very low probability of running into this.
Yeah. I guess you could also have like some sort of like Markov chain thing where like suppose you believe that rewards are like, you have some plan, right? Let's say the random distribution that produces worlds says that like, there's some reward at the start, and then like, you randomly generate a reward at the next step, that's like, let's say mean the previous reward time step, with some variance. And then like you randomly generate the next reward based on the previous reward, then you randomly generate the next one based on the previous one. And somehow like, the only probabilistic dependence is step by step. And then it would be very unlikely for you to have like, then, the best predictor of like what your life is like in 10 years is what your life is like at 9 years. And it's very unlikely that what your life is like in 1 year is a better predictor than what your life is like in 2 years. So that's, yeah, I'd have to think a little bit about how exactly to write that down, but it seems like that's one semi-natural way you could do that as well.
Yeah, that I like that. Yeah, I mean, we'd have to work out the details, but it sounds at least better than the things that we came up with.
Yeah, it feels like, yeah, maybe I'm over anchoring on this one counterexample, but it feels like the weird thing about the counterexample is somehow miraculously, like your first like instinct, even though it isn't very important, it like, is the best predictor of the future. And like, do you have any other counterexample? Ideally, you'd have three like this is like the test-driven development thing, right? I worry that I'm overfitting to this one example.
I don't think I have like, fundamentally different ones. I think I mean, it's possible that kind of other issues would come up, but I think the main issue is really kind of like just stumbling into the bad behavior. And I think, I don't have any other ones.
Before we wrap up, the final thing I want to ask is, suppose people listen to this, they're interested in your research, how should they follow it?
Yeah, so you can follow my personal research. I have a personal website that's just davidlindner.me, my first name, last name.me. I'm on Twitter or X, David Lindner. And then you can follow kind of our work at DeepMind. We have kind of a Medium blog where from the alignment and safety team where we publish kind of blog posts often about our recent papers. And we also I post, and like other team members post on the alignment forum pretty often.
Yeah, if people want to check that out, links to those will be in the description. David, thanks very much for joining me.
Yeah, thanks for having me. That was very fun.
This episode is edited by Kate Brunotz, and Amber Dornace helped with transcription. The opening and closing themes are by Jack Garrett. The episode was recorded at Far Labs. Financial support for the episode was provided by the Long-Term Future Fund, along with patrons such as Alexei Malafeev. To read a transcript of the episode, you can visit axrp.net. You can also become a patron at patreon.com/axrpodcast, or give a one-off donation at ko-fi.com/axrpodcast. That's ko-fi.com/axrpodcast. Finally, if you have any feedback about the podcast, you can email me at feedback@axrp.net.